Okay, let's get started. So section 3.1 on estimators is the essential building blocks for the whole chapter 3. An estimator is the function we call an estimator that computes the estimates. So we need a name because, for example, the sample mean is a number. But how did you compute the sample mean? You use the calculation, sum all the values together, 1 over n times the sum of the values. So this process of computing the sample mean, we want to have a name for the function that computes the sample mean. So that's where the concept of estimator comes in. Okay, so this is the book, and I have prepared a very detailed notebook with all the code examples from the book. So we're going to go in parallel with the theory and the practice. Okay, so why are estimators important? Because they're the cornerstone or the essential building block for all of the chapter. So in the next section, we'll talk about confidence interval, and the remainder of the chapter we'll do hypothesis testing. And all of these applications depend on your knowledge of estimators. Okay, so the concept of an estimator and the sampling distribution, if you understand that, then all of statistics will be super straightforward. Okay, this video is going to be very high level because I previously tried to record a more detailed video and it took an hour. So I'll let you read the PDF for details, but in this video I just want to give you a walkthrough of the material. So we have the book, we have the notebook that shows all the code examples. This is just some basic setup which we can skip. Okay, this is just sales pitch. You know, if you do the estimate, if you understand estimators, then confidence intervals and hypothesis testing will all be straightforward. Okay, definitions. Because the data chapter was hundreds of pages ago, I'm including a little review. So what is a population? What is a sample? The descriptive statistics, that's very important to remember. So here is the little table. What did we learn in section 1.3 is how to compute the sample mean, the sample variance, sample standard deviation, the quartiles, the percentiles, maximum, minimum, all of these things. When you have a given sample X, remember this boldface X means a sample of size n, we can summarize it using the descriptive statistics we learned in chapter 1. The goal of descriptive statistics was just to summarize. Given the sample, give me some numbers that describe it. In this chapter, so in chapter 3, we're doing something new. We're not interested in that sample. We're interested in the population. We're interested in generalization. So we assume this sample came from a population, and we're really interested in the population. So how can we infer the properties of the population based on a given sample? And I said here is the diagram, how this works. In order to do statistical inference, we need to first assume the probability model for the population and how the data was generated. So you need to know the probability model here. Okay, so again, this is why we did chapter 2. We happen to be expert, or at least familiar with, probability theory. So this is why we did all these details in the probability chapter, is because if you don't understand that, then statistics will just be blah blah blah. Okay, so quick reminder, I'm using this calligraphic M to describe the model, which could be, for example, the uniform, a Poisson exponential. So it's some shape of the data that describe the population, which we call the model family. And the parameters of that model In general, we call it theta, but you can think of this as the mean, the standard deviation, or for Poisson model, Poisson population, the parameter is called lambda. So when you assume the model family, then it takes different parameters. And these are the norms. So we assume the model is, let's say, normal, but we don't know the mean and the variance. Okay? Remember that computers are your friend. You can use, you can create computer models for any population family. This will turn out to be very helpful when running simulations. Okay? Little technical term, parametric inference refers to the fact that we're just trying to infer the parameters. Okay, so we assume the model is known. We're just trying to guess the parameters. Yada yada. Okay. New concept. All right. So the estimate is a number you compute from a sample. An example of an estimate is the sample mean. Okay. We said the estimator is the function you use to compute this estimate. And this is a new concept. We kind of saw it in chapter 2, but this now we're going to see a lot more of it. What is the sampling distribution? It tells you the same function g, the same estimator, but instead of computing it from a particular sample, you compute it from a random sample. So this little thing I've highlighted here hides behind all the probability theory you learn. So it's like a joint distribution over n random variables and describes all possible samples. So this is one particular sample, like you measured the weights in 100 individuals. This describes a theoretical concept of all possible samples of size n. Okay, so imagine you have that theoretical random sample, and if you compute the mean of that random sample, you get a random variable, right? Because if the input, if you're calculating the mean from a random sample, then the mean will be a random mean. So the distribution of that, the sample mean for a random input, for a random sample, that's called the sampling distribution. Essentially, we're not interested in one particular mean, but the set of all possible means you can observe from random samples from the population. Okay? And one way to quantify, to describe this distribution, the shape of the distribution, specifically its dispersion, is called the standard error. So this is a new concept. It's the standard deviation of this distribution. We'll see it in a second, but just introducing the notation, SE stands for standard error. And in a subscript, you say standard error of what? So this tells you that when you compute the sample mean from random samples, what is the dispersion? What is the variability of the sample means you can observe? Okay? So here is a table that tells you everything we're going to do in this section. Remember the sample mean we learned in section 1.3? Well, the function that computes the sample mean so this is a function that takes samples as input and produces the sample estimate. And the inference process tells you that if you compute the sample mean, it tells you something about the population mean. And similarly, the sample variance tells you something about the population variance. The standard deviation is just the square root of the variance. And there's a new analysis, which is very common in statistics. You have two groups, and you have the sample from one group, and you have a sample from the other group, and you can compare it. So this is the difference between means of two groups. And the population parameter, it's actually a composite thing. So you have the population of one group, the mean of one group, the mean of the other group. So we're estimating the difference between the population means. Okay, so except for the word estimator, there's nothing new here. If you look at the reminder, what we learned in section 1.3, you have seen this stuff before, right? The sample mean, the sample variance. The only difference is what we're using them for. So instead of just summarizing the properties of a given sample, we're going to try to make inferences about the population. I like this phrase. Everything you learn in descriptive statistics, it's going to be actually the same math. So there's no new, I'm not introducing a new concept all of a sudden. Like the sample mean, you know how to compute the sample mean. But the applications we're giving them is inference about unknown population parameters. Okay, a little notation. So I'm going to use the hat on top. This is a convention to describe estimates. So the population parameter is theta, and theta hat is a quantity computed from the sample X. So estimates will have little hats on top of them. However, for the sample mean, because we already introduced it earlier, we're going to stick to the notation from chapter 1. But if you wanted, like technically, if you wanted to express using the hat notation, you could say, right, because this is an estimate for the population mean, we could say it's mu hat. And the sample variance is sigma squared hat. So hat means estimate of. Okay? Yada yada. Okay. Sampling distributions. Okay, there's a nice picture here. Let's look at the picture. Because all of this is in your head. How can I say this? It's a theoretical construct, right? So the only thing that exists is a sample. But we assume the sample comes from a population. And the estimate theta hat, right? So this is the function. So given the sample X, we compute an estimate theta hat. Okay? The examples of estimates, I said sample mean, sample variance. Okay? Right. The estimator function, I'm going to use the names very descriptive, mean, vars, std. So these are functions. And when talking in general about all estimators, I'm going to use the generic name G. I chose G because it's the standard name we use for functions, so it tells you the estimator is a function of some sort. All right. Yada yada yada. Okay. So let's go a little bit dig into the three, because this is the section 3.1. We'll spend a lot of time on these estimators. So the mean, the variance, standard deviation, and the difference between means. So let's look at it, the formula. Okay, so what is mean of X? Is the sum of the values in the sample divided by 1 over n. So this is the math definition. And let's look at it in code. The sum of the values in the sample divided by n. Okay, let's try this out. You know what? I'm going to run this. Okay, so the Python function. So, reminder, estimators are functions that take samples as inputs. And to make this really explicit, I'm going to define a Python function with the same name as the math function that does this operation. So let's say the mean of a sample, this sample, oh, that's going to be an error. So what is the mean? Let's say 1, 1, 2, 2. So the average of the sample should be 1.5. I think so. We'll get it so there's a bunch of heavier computations lower in the notebook, so that's why it's taking a little bit of time. Okay, so that's the sample mean. The other estimator is the variance. The A takes a long time. The variance, we saw that already, the sample variance, we saw that already in the section 1.3. Again, nothing new. You first compute the mean, then you calculate the square deviations from the mean for each observation, and you divide by n minus 1. So this is a key step here. You don't divide by n, you divide by n minus 1. We'll finally get to explain why we're doing that in the end of this section. So bear with me for now, just trust me, it's 1 over n minus 1. Okay? And here is the Python function that performs the same calculation. So you compute the sample mean. Here is a list of all the square deviations from the mean. We sum them together and divide by n minus 1. Okay? Little comment. After, in the real world, after this class, you can use the pandas method mean or the numpy method mean. So you don't need to use your own functions to compute. But for heuristic purposes, because I want you to learn, yay, finally it loaded. Okay, and I'm gonna clear all outputs, yeah, just so we can see things one by one. Okay, so we're going to use all the examples, we're going to use our own function mean. Okay, but keep in mind there are other options, like pandas provides a way to compute means, similar for the variance, and in NumPy also provides ways to compute all of these things. But you know, explicit is better than implicit. Okay, standard deviation, scrolling down, you just compute the variance and take the square root. Not super exciting. Okay, first example. This will be easier here. Okay, so I have here a sample of apple weights collected from an orchard, and we're interested to know what is the sample, what is the average weight in the population. Okay, so this is a data frame, and by calling it, like by extracting the weights variable, so this is a column of the data frame, the object you get is a pandas series. Okay, let's take a look at it. Okay, so these are the values of size 30 of a sample of weights from the apple weights, so that from the orchard. Yada yada. So little details that under the hood the sample is stored in a NumPy array. Not super important. Here is an easy way to visualize it. Okay, so we just plotted. It's called a kernel density plot. Basically, we a smooth curve of the samples. Here is another way to visualize. Hist plot of a sample. Okay, so we see there's the average is around 200. You see some large apples, some smaller ones, and you see this depending on the number of bins. Let's say 30 bins, 20 bins, 10 bins. We're going to see more or less detail. So the KDE plot is a convenient. It just smooths things out. You don't need to choose how many bins to plot. So yeah, quick. This is what the data we have. Okay, now let's start to compute. Yada yada. Just make sure I'm following along. The sample size. Well, let's compute the mean. Okay, and this is the variance and the standard deviation. Okay, so what am I doing here? I'm calling the function I just defined above. And similarly here, we're calling the functions our own functions for calculating the variance and the standard deviation. Of course, pandas gives you the describe method, which can do all of these calculations for you. So you see we get the same values, standard deviation. You can do it all in one shot. Okay, And this is something new called the standard error of the estimator, which we'll talk about in a second. Okay? This shouldn't be here. It comes later in the section. So just ignore that. Okay? Last but not least, the difference between means estimator. Okay? You take, you have two samples now. One sample from population X and one sample from population Y. So compute the difference of the means. Literally, you compute the mean in the one, compute the mean in the second one, subtract. We call that D hat. So D for difference and hat, it's an estimate computed from the samples. Okay, so for that we need a different data set, the electricity prices. So this thing contains, if we look at it, so this is a data frame again that contains prices from 9 samples from the east end, east and west, so these are 2 parts of the city, and another 9 samples from the west end. So this is the standard tidy format that you have 1 observation per row. Okay, I'm gonna hide that because it takes too much space. Okay, so now in case you don't remember, so let's say we actually want to have 2 separate samples. I want to have the east end prices, this data here, in its own variable, and separately this data here. Okay, so how do we do that in NumPy, in Pandas? You say select all the electricity prices where the end column is equal to east. Okay, we're doing west first, I guess. Okay, so this thing is called a Boolean mask. It says a true, 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 and false, 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 false. Okay, and then using that mask as the input to ePrices, we'll select only the rows 9 through 17. Okay, and we store that in ePrices. And then you'll see we just got this data here. Okay, the mean and the variance of the sample, you know, from here on we just saw what it did. And we're going to do the same thing for the east end prices. So we'll select the ones that are end east, and and we extract the price data. Okay, same procedure, but for the east end prices. Here are the 2 means. The average price in the west is 9.15 cents. The average price in the east is 6.15 cents. And the interest, what we want to know is the difference between the means. And that's why we define this estimator, the difference between means. So we just call it, and to compute the difference between these 2 numbers. So 3 cents on average. So far nothing new here. We're just computing summaries of the samples. We're computing estimates. And the estimate tells us that the average price difference between the west and the east is 3 cents. Okay? And now we get to sampling distributions. Okay, here's a bunch of exercises which I want you to try. So if you go, there's a link, but the link will take you to exercises 31 estimators. I just want to show you this because the learning experience will be much better if you try things on your own. Exercises for section 3.1. So I've copy pasted the functions for you, and I have set up a little, like, so you don't have to copy paste the boilerplate every time. But you see all of these places are for you to complete. Okay, so I hope you click on the link for the exercise and try this on your own, because trust me, this is a complicated chapter, complicated section, and it will really improve your learning if you try things on your own. All right, sampling distributions. You know what? I'm gonna cut now and start a separate video because this is a big topic. All right.